Okay, for this recording, I'm going to focus on a few learning outcomes, which I think very highly likely will come up in your paper too. So you can see that I highlighted 1, 2, 3, and 4. State the names and formula of common acids limited to HCl, H2SO4, HNO3, and also ethanoic acid. Second one is you have to state the names and also formula of common alkalis limited to sodium hydroxide, potassium hydroxide, and also ammonia. The third one, you have to be able to describe the Bronsted-Lowry theory of acids and bases. Then number four, you must be able to describe strong acids and strong bases as fully dissociated in aqueous solutions, and also weak acids and weak bases as partially dissociated in aqueous solution. So the first slide, okay, I put in the names and formula of the common acids and alkalines that you are required to know the formula and also the name. So the first three acids, hydrochloric acid, sulfuric acid, and nitric acid, they are strong acid. Okay, the last one, organic acid, ethanoic acid, is a weak acid. So they only limit you to know all this. So make sure that you know the formula and also the name. For alkali, sodium hydroxide, and KOH, potassium hydroxide, they are strong bases. And there's only one weak base that you are required to know. Sorry, weak base. Okay, so the first three acids, they fully dissociated in aqueous solution. Ethanoic acid is a weak acid, so it partially dissociated in aqueous solution. Same goes to strong bases. They fully dissociated in aqueous solution, and ammonia partially dissociated in aqueous solution. Right, so I have the definitions here. Acids, strong acids, they are fully dissociated in aqueous solution. Weak acid, they are partially dissociated. Strong bases fully dissociated in aqueous solution, and weak bases partially dissociated in aqueous solutions. Now, there's another theory of acids and bases, Bronsted-Lowry bases. Okay, Bronsted-Lowry theory of acids and bases. So, a Bronsted-Lowry acid is a proton donor, and a Bronsted-Lowry base is a proton acceptor. Now, in an acid-base reaction or neutralization, a proton is donated by an acid and accepted by a base. Right, so I've covered 1, 2, 3, and 4. Now let's go to number 9, which is to sketch the pH titration curves of titration using combination of strong and weak acids with strong and weak alkalis. Now, since we have strong acid, strong base, then the weak base, so there are 4 types of combination we can make from out of these 4 types of acids and also bases. Strong acid versus strong base neutralization, weak acid versus strong base neutralization, strong acid, weak base, and then weak acid and weak base titration. Now, every titration curve has a very common sigmoid shape like this, okay? A S shape like this. Sometimes it's a reverse, depending on you start with which solution in the conical flask. If you start with acid in conical flask, so the pH is low, below 7. You know that acids, they have pH less than 7. Then base, at the end, we have base in excess. So the pH will be higher than 7. Okay, so for a titration, the pH change shown by this graph, okay, starting with acid in conical flask, so pH is lower than 7. So slowly adding alkali to the acid solution, the pH will rise slowly. It rise slowly because the H plus in the solution is neutralized by the hydroxide ions from alkali. And the last drop into the conical flask neutralize all hydrogen ion or protons. So pH will go up to 7 for strong acid and strong base titration. This is a weak acid and strong base titration. That's why the endpoint, the pH is more than 7, which I'll cover later. So, but anyway, okay, uh, the pH will go up quite suddenly, drastically, because one drop neutralizes all the proton ions. And when you add one more drop of the alkaline, the pH is now more than 7 because now you have more hydroxide ions in the solution. So the pH will go up to more than 7, and then you add more and more sodium hydroxide. Can you see here the x-axis? More and more sodium hydroxide. So the pH at the end is the pH of the sodium hydroxide solution in the mixture. Okay, so this is the common shape of a titration curve. Now we have 4 types of titration, right? Strong acid versus strong base titration, strong acid versus weak acid versus strong base, weak acids versus versus weak base. Now you will be asked to sketch a pH titration curve in paper 2. So the first thing that you need to do is you have to identify the acid and base which are given to you in the question, whether it is a strong acid or weak acid, and the base is a strong base or weak base. Now, if it's strong acid versus strong base titration, let's say HCl and NaOH, so the titration curve will look like this. Okay, quite flat at the beginning, starting with acid in the conical flask. So pH is 1. For strong acid, we start with the pH lower than 2, usually 1. Look at this strong acid versus weak base. With strong acid in the conical flask, also we start with 1. Okay. Now the pH will rise slowly, very very slowly. That it is almost flat. Then until the last drop NaOH being dropped into the conical flask, pH go up to 7. Okay, for strong acid strong base titration, the equivalence point is at pH 7. One more drop of sodium hydroxide. Now sodium hydroxide is in excess. In the solution, we have a lot of hydroxide ions, but no more H plus ions. So the pH will go up. And then when you add more and more sodium hydroxide until it is in excess, okay, at the end, pH is 13. So if you end with a strong base, at the end, the pH must be more than 10. Okay, I'll say 13 is the safest. Okay, now let's look at strong acid versus weak base titration. So again, we start with acid in the conical flask. So pH is 1, just like this case. pH is 1 because we start with strong acid in the conical flask. So this time we are using weak base, for example, ammonia. Okay, so slowly flowing ammonia solution from the burette into the conical flask. So the pH will slowly rise until here, one drop of ammonia neutralizes all, okay, all the H plus ions in the solution. So pH will go up, but in this case, the equivalence point is less than 7. Okay, because ammonium salt is formed and ammonium ion can dissociate in water in solution to give a little bit of H plus ion. So the pH is slightly lower than 7. Okay, let's put it as 5. Okay, just an approximation. So to be safe, you put it as the pH less than 7, 5 or 6, okay? Then another drop of ammonia, now you have more hydroxide ions in the solution, so the pH will go up, okay? But remember, this is a weak base, so at the end, okay, when ammonia is in excess, the pH will not be higher or as high as the one as like in a strong base solution. So it should be lower, okay? So I would say 10, pH 10 is more reasonable. This is 13 for strong base, okay? So here will be less than the 13, okay? To be safe, less than the 11. So I say 10 would be the best answer. Next one, let's look at weak acid versus strong base titration. Next time we start with weak acid. Now compare weak acid and strong acid. Weak acid partially dissociated in aqueous solution, so you have lower concentration of hydrogen ion in the solution. So we should start with a pH not the same as strong acid anymore, should be higher. So start with 3. Okay. And strong base sodium hydroxide. So start this titration by adding sodium hydroxide into the weak acid, ethanoic acid, for example, in the conical flask. So the pH again will rise, but this time pH will rise much faster compared to a strong acid because you have less hydrogen ion, right? And you see that it's not as flat anymore. You have not learned this, you are going to learn this in A2, but there's a buffer region here, so it makes this part less flat, okay, more like uh, you have a steeper curve at the beginning, then slow down, okay, go up again when equivalence point is almost reached. And one more drop of sodium hydroxide ions in excess. Okay, now the end, at the end when sodium hydroxide is in excess, you have the pH of sodium hydroxide solution, just like the one in strong acid versus strong base. Okay, 13. And this one, the equivalence point is more than 7. Okay, because the ethanoic ion in the solution will actually hydrolyze by the water and form a bit more of hydroxide ions in the solution. Okay, so the pH is more than 7. Now, there's another one, the last one, weak acid versus weak base titration curve. Okay, here you see that it's the combination of this part and this part from the other two curves, right? Because we have now weak acid, okay, weak acid, so this part will be the same as a weak acid, and the last part will be the same as a weak base. This graph, okay, is unique because it doesn't have a vertical region like the other three curves. If you look at the other three curves, you have the vertical region, right? Because you have the sharp change in pH neutralization. But because we use weak acid and weak base, okay, the vertical region is not significant. Okay, it's not obvious. But equivalence point is still 7. pH equals to 7 for equivalence point. So this very unique titration, the pH change cannot be indicated by a pH indicator. We need to use a pH meter, for example, to detect the endpoint. The other three will be able to use a pH indicator to tell us when do we need to stop titration. So again, right, you must be able to draw these uh, 3 different curves. Okay, I doubt that they will ask you to draw this one. So these 3 different curves. First, you need to know whether it starts from acid or base at the beginning. All my curves here start with an acid in the conical flask. Okay, so we start with acid pH, then go up. Okay, a little bit more flat for strong acid. Okay, uh, a bit more curvy for this weak acid. Then they all have a vertical region for sharp change, sharp increase in pH, and at the end, the pH will be the pH for the type of base in the titration. Okay. Now, there are two questions when the syllabus changed. Summer 2022 and also March 2022 asked the candidates to sketch a graph to show the titration curve. Okay, I'll come to this later. We start with slightly um, more straightforward type of question. Now, I took this from paper 4 because these learning outcomes, they were used to be in paper 4. So I have this simpler question from paper 4. They gave two titration curve. Now, can you see that this sigmoid shape is the reverse from the curves that I've shown you? Okay, because we start with pH more than 7, meaning, okay, start with basic solution, alkaline solution in the conical flask. So you are adding acid into the base. That's why this time the pH will drop. Start from basic pH, then the whole titration will end with acidic pH because acid will be in excess at the end. Now, so what does this question ask for? Use the titration curve. You are supposed to deduce the volume of acid added at the end point for this titration. Now, where do we know where's the end point? Okay, the end point will be the equivalence point. So you find it in the vertical region. So y-axis will be for pH change, x will be volume of acid added. They want you to find the volume of acid added at the end point. Now, vertical region is where the end point lies on. So from this vertical region, go all the way down. Just draw, right? For M curve, right, this is 28 centimeter cube. And for N, go down, this will be 42 centimeter cube. So that is how you deduce the volume of acid added at the end point for a titration. If you are given a titration curve like this question. Okay. Now, again from paper 4, I have a question. Let's just look at the question. A 10 centimeter cube sample of amino ethanoic acid. You look at the name ethanoic acid, right? I know there's an amino here, but still a carboxylic acid, so this is a weak acid. This weak acid was titrated with sodium hydroxide. Okay, this is a strong base. So whenever you are given a question like this, you identify the type of acid and base used in the question. Sorry, it should be a base. So weak acid titrated with sodium hydroxide. When we do titration, okay, something in the conical flask is titrated with another thing in the burette. In this case, weak acid is here. Sodium hydroxide is in the burette. Okay, so that means we should start with acidic pH because you are measuring the pH in the conical flask, not in the burette, right? Because you're going to mix these two solutions in the conical flask. So you can only measure the pH change in the conical flask. So we start with weak acid. So when sodium hydroxide is added, then the pH will slowly rise until the end we have the pH of sodium hydroxide in excess. So, okay, you can pause this video, but think about you should draw a titration curve with the shape of number 1 or number 2. Okay, so I'm going to review to you the answer since I've already drawn the titration here, you start with weak acid and then titrated with sodium hydroxide. So you should start with acid pH, and at the end with the pH of a strong base solution, which is sodium hydroxide in this question. Right, another question. This time you have isocyanic acid, and this question tells you it is a weak acid, right? And sketch how the pH changes during an addition of a total of 30 centimeter cube of barium hydroxide to 20 centimeter cube of isocyanic acid. So given this weak acid, so think about barium hydroxide, barium hydroxide. Is it a strong base or weak base? Okay, now this is a weak acid. Now if you can remember from group 2 hydroxides, barium hydroxide is very soluble in water, so it is actually a strong base. And again, right, you are adding strong base to weak acid. So again, this weak acid is in the conical flask and barium hydroxide in the burette. So you should again get a curve with the shape of number 1 because it starts with acid and it ends with a base. Now another question, again you are supposed to choose whether you get curve number 1 or curve number 2. Here we have a piperidine 11.9 pH, more than 7, right? And but less than 12. So this is a weak base. Now 20 centimeters of HCl was slowly added to 10 centimeter cube sample of this piperidine. So that means we have this time, okay, this piperidine in the conical flask and HCl in the burette. Okay, so which curve we should start with? Okay, 11.9 in the conical flask. So should be curve number 2. 11.9 here at the end. When HCl is in excess, you have an acidic pH. Okay, now we can look at the summer 2022 question. You have HCl added to a beaker and its pH is recorded. This time they are doing the neutralization in the beaker. They don't talk about burette and conical flask. HCl in the beaker, right? Then you have ammonia added to the HCl in 5 centimeter cube portion. So slowly add more and more and more until 50, right? So you are supposed to sketch the change in pH which occurs when HCl is titrated with NH3. So step number 1, identify acid and base. Strong acid or weak acid. Okay, HCl is a strong acid. Ammonia, strong base or weak base. Okay, from the list, the name and the formula at the very beginning just now, we know ammonia is a weak base. Okay, so now we have identified, okay, so this should be a strong acid versus weak base titration. So the type of graph, okay, let us see. We should start from acidic pH or alkali pH. Ammonia is added to the HCl. Okay, so start with acidic pH that ends with basic pH. So the curve should start from this one. So this is the sigmoid shape that we wanted. And then, okay, so what do we do next is, okay, you have to find the volume, okay, the volume of the endpoint. So here HCl 25 centimeter cube, 0.1 mole per decimeter cube. So let's find the number of mole of HCl, which is 25 times 0.1 divided by 1000, okay, which is 0.0025 mole. Am I right? 1, 2, 3. Okay, correct. Now, if you write an equation to show the neutralization between HCl and ammonia, you realize that the mole ratio of HCl and ammonia will be 1 to 1. So the number of mole of ammonia is the same as the number of mole of HCl, which is 0.0025. And the concentration of ammonia is also the same. So the volume of ammonia to neutralize 25 centimeter cube of HCl would also be 25. So that means this vertical region will be at 25 centimeter cube, which is here. Okay, so I just will draw one straight line to go up. Sorry, it's a bit not so straight. I'm drawing it freehand. Okay, now we have all the information needed to sketch the curve. 25 for equivalence point. This is strong acid versus weak base titration. So at equivalence point, the pH is less than 7. You always follow the one that is stronger. So in this case, strong acid versus weak base. So pH is leans more to the strong acid. That's how I remember the pH of the equivalence point. So less than 7, I'll say 5 maybe. So this one will be the middle point of the vertical region. Now we start with a strong acid. So again, if we start with strong acid, we start with pH 1, okay, as the starting pH, and weak base, so should end with about 10 or 11, 7, 8, 9, 10. Okay, I'll say end here. Okay, so let's start drawing the vertical region first. So the middle point is here. So if I want the graph to be like this long, okay, so this middle point, now I have to join all this together to get the shape. Sorry. So now I have to join everything together, okay, to get this sigmoid shape. Draw. Okay, then go up. Right, so this will be my sketch for the titration for this HCl and ammonia. So let's check the answer. 2 marks for this question. First, you have the correct basic shape extending to 50. Oh, did I extend to 50? Oh, let's check. I didn't, right? Okay, so you see, I didn't extend until 50, I'll lose the first mark. So be very careful. Okay, it says 50, so we should extend until 50. My mistake, I didn't check that. With vertical portion of curve at 25, right? 25, okay? So remember, this is very important. Second mark, initial pH at 0 to 2, because HCl is a strong acid, right? So 1 is the safest, so I start with 1, which is correct. And final pH between 8 to 12, because ammonia is a weak base. Okay, so again, this is correct. So if I've extended my graph to 50 just now, I've gotten both the marks, right? So I have another question here. This time, you are given 2 graphs. So you are supposed to sketch 2 pH titration curves. Now, so I want you to try, okay, by yourself, and you can pause the video to try to solve this question, sketch your curves. Later I'll show you the answer. So go back, look at these steps that you're supposed to follow. Strong acid or weak base. Okay, strong acid or weak acid, strong base or weak base. Okay, so one is sodium hydroxide with HBr, another one is NH3 with HBr. You are given the concentration and volume. Okay, now let's look at the answer. First mark, correct sigmoid shape with vertical section at 25 for both. So the first one is always given to the shape, correct shape, okay, and also the volume for the endpoint. Okay, this one they didn't give you the volume of the base added to the acid, so okay, there's no mark given to extension of graph until 45. And both curves shows initial pH less than 2. Both HBr, okay, both are using HBr. So HBr is a strong acid. That's why you have to have initial pH less than 2. And the third mark for sodium hydroxide, the pH more than 12, and H3 pH 8 to 12. So the shear graph should look like this, both 35, 35, up, 35. Now this is strong base, weak base. This is strong acid. This is strong acid. Strong acid versus strong base. pH more than 7, sorry, pH equals to 7 at endpoint. Weak base, strong acid, pH less than 7. So it's the middle part, middle, okay, middle, middle. Strong base, so pH 12. Weak base, okay, pH less than 12, less than 10. Start with strong acid for both. Start with 1. Okay, I can accept a little bit more. So go up and go up. Weak base, okay, we'll go up slightly more curvy compared to that one. Sorry. Okay, then go up. Right. So okay, let's go up. Strong acid, so it's a bit flat here, but here we have a big base, so more curvy compared to the strong base. Okay, so you can see the difference between these two. Okay, and at different pH, this is lower, this is higher, and then both have vertical region, both at the same pH, but different pH of the endpoint. So this is how you get the 3 marks. Okay, now I want to go to the last part of this recording, which is to select stable indicator for the acid alkali titration. This is new in the syllabus and hasn't been asked in paper 2 since summer 2022, March 2022 to be exact. So I think that it might come out this time. So how do we choose indicator for a titration? We look at the vertical region. Okay, if the pH, the color change of that particular indicator falls within the vertical region, we can use that indicator Okay, we can select the indicator to be used in the titration. So again, I've got these four curves for different titration. So to select the suitable indicator depending on the vertical region, I'm just go straight into example. So if I have strong acid versus strong base titration, and I have three indicators to be chosen from phenolphthalein, litmus, and metal orange, but you can see that all three of them they change color, okay, within this vertical region. So they can all be used for the titration. Of course, don't use all of them, just select one. If you are given a question, a curve like this, and you are given these three indicators, you can choose any of them to be the indicator. Okay. Let's go and look at the second type of titration curve, strong acid versus weak base. Metal orange, litmus, and phenolphthalein again. Okay, so for metal orange, the color change falls within this vertical region. Litmus slightly borderline, phenolphthalein is totally out. So the best indicator of these three will be metal orange for this titration. Next one, weak acid versus strong base titration. I have again these three indicators. You can see that phenolphthalein is the most stable one because okay, the range for the color change falls within the vertical region of this titration curve. And the last one, weak acid, weak base, right? It doesn't have, this titration curve doesn't have a very wide, okay, very obvious vertical region. Therefore, weak acid, weak base titration can, the end point cannot be determined by using a pH indicator. Okay, it can only be indicated by pH meter, a tool, a machine that we can use to directly measure the pH of the solution. Okay, now let's look at the question. Now, in the question, they will not give you a very nice diagram like this. Okay, for you to choose the indicator, they only give you a range. Okay, a pH range for the color change of the indicator. So, for example, this question, you are given the curve. We are given four different types of indicators and the pH range for the color change of this indicator. So for malachite green, 0.2 to 1.8. So let me plot 0.2 to 1.8. Sorry, 0.2 should be lower, right? 0.2 to 1.8. I would say until here probably. So malachite green change color within this region, right? So you see it's totally out of the vertical region here. So we cannot choose malachite green as the indicator. Now bromo creso green 3.8. Okay, 3.8 should be here. 5.4. Where is 5.4? Is 5? 5.4 is here. Okay, now it falls between. Okay, falls within the vertical region. Bromo creso green can be used as the indicator for this titration. Now what about bromo timo blue? 6 to 7.6 will be around here. Okay, also falls within the region. Yes, can be used. Timophthalene 9.3, 9.3 is here. 10.6. Okay, out of the region, no, this cannot be used. So for this reaction M, we can choose bromo creso green or bromo timo blue as the indicator. I just choose one, right? So bromo timo blue or bromo creso green. Now let's look at reaction N. Okay, same type of same group of indicators for you to choose from. So again, okay, you can pause this video and try to put in the range on the vertical region and see whether they are within the vertical region or not, and then you choose an indicator, a suitable indicator for reaction N. Okay, pause this video. I'll review the answer after a few seconds. Okay, so for reaction N, okay, you have bromo, you can use bromo blue or thermophthalate. Okay, because these two, the pH range, okay, falls within the vertical region. Now you need an explanation, right? The explanation is what I've been repeating, okay, because the indicators have a pH range, okay, or color change within the vertical region of the graph of the curve, the pH titration curve, right? Okay, so that is the end of this recording. So just recap a little bit. I've covered a few learning outcomes here, which I think I predicted to be asked in the paper two in this winter 2023 uh, series. Number one, number two, three, four, 9, and 10. Okay, so you look at these learning outcomes again. If you think which part of them you are not quite confident yet, then please just go back to the part in this recording, rewatch the part and master it before your paper two. Okay, good luck for your exam.